All right, so tonight we're looking at the Unit 11 review packet. Number 1 is D, because light is refracted as a result of its change in its medium's velocity. In fact, frequency stays the same during refraction. Think like my red frequency light is still red if I put this, underwater. And angle and wavelength change because velocity has changed. For number 2, all of the following images can be made by either converging lenses or mirrors, except for real, upright, and larger. And the reason is all virtual images are upright. All real images are inverted. You can't have a real upright image. Concave lenses cause parallel rays of light rays to diverge. A good picture to have in the back of your head for this one would be your parallel rays of light going away from a focal point. That's the definition of diverge. All these light rays are going away from a virtual focal point located somewhere back here. Similarly, concave mirrors cause parallel rays of light to converge. Now, small typo here. A concave lens hits a lens, concave mirror hits a, this should say mirror. And the picture I have in the back of my head for this would be parallel rays of light obeying the law of reflection, so bouncing off this medium towards a focal point, off this medium towards a focal point, so it causes the rays to converge. Now, the focal length and center of curvature are related to each other in that the focal length is half of the distance of the center of curvature. Or let's say it the other way around. It's D. The radius of curvature is twice as long as the focal length. And perhaps better wording for this might be the focal length is related to the radius of curvature because the radius of curvature is a distance and the focal length is a distance. The center of curvature is the point. In this case, my center of curvature is twice the focal length. It's the point at the center of the circle caused by this lens's edge. So an object that's placed in front of this lens at a distance less than f. Now, you can totally draw out your ray diagram here, or if you have this memorized, you could also do that. So a ray would go parallel in towards the focal point, because this is converging. A ray would go from the top of my handle through the vertex. But the two real rays, they don't meet each other. Well, that must mean that when our eye sees these two divergent rays, it extrapolates backwards. Brains are really good at pattern recognition, and they're like, brain, if these two diverging rays came from the same place, then my image must be this big image of a candle out here. That is a virtual upright larger. Now, strategy, guys, if you can do open notes on this, you could write out all the different types of images that are formed by different configurations of converging or diverging devices. That way you don't have to ray diagram or calculate, something that you could simply check your notes against. Now, for your test, assume that we will have the rays drawn for you, so parallel in, towards the focal point. Assume we will have the rays drawn for you because there's not a great way for us to test that skill while we are at home. This ray would go through the vertex. And since this top of the candle is located at this intersection here, this would be an inverted, real, smaller. And if you're having trouble with this M notation, M is smaller than 1, so my image is smaller than my object. Now, what type of image is formed when an object is placed 1.5 focal lengths from a converging lens or mirror? So, in this case, We could do this mathematically. We could do DO is equal to 1.5 and set my focal length equal to 1 and solve for DI. You could totally do that. That would use the Lensmaker's equation to solve for DI. That's 1 over 1 is equal to 1 over 1.5 plus 1 over DI. We could make a least common denominator of 3, so that's 3/3 minus 2/3 equals 1 over DI. 3 minus 2, that's 1/3 equals DI, or DI equals positive 3. DI being positive means that that is a real image. So it can't be A or B. Real images are always inverted. D. Now, other ways you can do this, you can check it on a chart that you have in front of you that you've written from your previous notes. Or if you want, you could go draw a sketch of this ray diagram to get the same answer. In the diagram above, the image of object B would be converging, so it goes parallel in and towards the focal point. Then it goes through the center of curvature. Because it's a mirror, doesn't go through the vertex. And since these two rays diverge, our brain thinks that this image is formed back behind the mirror. If the top of my arrow is here, this makes a virtual enlarged upright image D. On a convex mirror, I actually don't need to draw anything for. Convex mirrors and other examples of diverging devices only ever make one type of image. It's always virtual, smaller, upright. D. Do expect that I will have you use the Lensmaker's equation. So you might want on Thursday's assessment to have out some sort of piece of paper to take notes so you're not trying to do this in your head. The image distance, DI, is what we're looking for when the focal length is 10 and the object is at 30. So let's do least common denominator here. That's 3/30 minus 1/30 is equal to 1 over DI. That's 2/30 equals 1 over DI. Therefore, DI is equal to positive 15. Be careful on the wording here. We really mean this to just say converging. Right? So I will try and make that edit in a place that you guys can see it sooner rather than later. Assume it's converging. If it's converging, then this focal length is positive 10. Here's the opposite question. This says the focal length is 10 centimeters, but we are being purposely tricky. This is diverging. So even though we said it's 10, like the absolute value is 10, when I substitute this in, diverging devices have a negative focal length. So I'm doing the same math here. Still 1 over DI plus 1 over DO. But this is negative 10 centimeters is equal to 1 over DI plus 1 over 30. You know how to do this. Least common denominator this. This is negative 3/30 minus 1/30 equals 1 over DI. That's negative 4/30. And guys, even I don't do this in my head. So make sure that when you're doing this on Thursday, you bring your calculator, you come prepared. Don't try to do this all this math in your head, right? So this is DI is equal to negative 7.5. That's B. 13. As the angle between the electric field and the transmission axis increases, that means, let's draw a picture here. Let's say I have vertically polarized light and it's going through a vertical filter. That means that it starts with all of the brightness. It starts being 100% bright. It's letting through all of these light rays. And then it gets dimmer and dimmer. So the component of light that passes through the polarizer decreases and the brightness decreases as well. So if you looked at light through a lens from two polarizing sunglasses that were overlapped at right angles to each other, none of the light would pass through. So let's draw out this picture for a sec. Let's assume I had a vertical filter and a horizontal filter. And I had unpolarized regular light to start, right? It would let through the vertical light and stop the horizontal. So the horizontal doesn't make it past the vertical filter. But the vertical light doesn't make it through the horizontal filter. So my eye being on this side, seeing no light pass through both filters, would assume this color is black. So the lens in a human eye is convex, and therefore the image on the retina is inverted. Cool. So 16, variation of the focal length of the lens in order to form a sharp image on the retina is called accommodation. And this is where the ciliary muscles change the shape of the lens in order to cause that image to focus on your retina. 17, what is not a primary color of light? Yellow. We literally call the additive colors of light the RGB color process, so it's not yellow. It's red, green, and blue. One for each one of the cones that occurs in our eyes. Let's say your eye does this. Right? If your eye does this, this is not focusing light in the correct place. This is focusing light in front of the retina instead of right on it. Now, this is problematic. If that occurs, that means you get this blurriness in your image, which means it activates more of those cone and rod cells than they're supposed to. Your image is there, but it's blurry, and so your vision is blurry. So what you would do is you would cause this light to diverge just slightly. Remember, a diverging lens takes parallel rays of light that come in and bend them slightly apart. Now, you only have to do this slightly. You wouldn't want it to go full diverging here, right? You just want it to bend apart a little bit to bring that focal length farther back. If I put a convex converging lens in front, that would actually cause it to focus harder, more extremely, and it would bend light more extremely. It would bring your focus out here, even more out of focus. How our eyes use these processes then is our eyes are easily tricked. A television or a phone screen can simply use red, green, and blue light to make our brain think we're seeing a bunch of colors. Great video on this, better than I'll be able to explain in 10 seconds or less. Please look up the video for number 19. It's called This Is Not Yellow by Vsauce. We trick our brain into seeing other colors because yellow photons, real actual yellow waves, right? Like if I had maybe not this banana. This poor banana is not actual yellow anymore. But maybe like this part of the banana. It's yellowish, right? Kind of yellow. Those are real, literal yellow photons of light hitting my eyeballs. But your brain is seeing fake yellow. Your brain is seeing this on a screen and is seeing a combination of red and green. It sees some red light and some green light, and your brain thinks, aha, yellow. Even though no actual yellow light is going into your eyes. How you do a problem like 21 and 22, these are called apparent color problems, is we need to know what each of the composite colors of light is made of. When this is white light as a source, that's some green, some red, and some blue leave my light bulb, and they hit the magenta duck. Well, hey, magenta is made of red and blue. There's actually no magenta on this spectrum. Magenta is what our brain thinks when it sees some blue and some red together. Just like purple, which is not a real color. My blue light reflects off the duck, and I know that's not obeying the law of reflection, but bear with me. And red light reflects off the duck because magenta is made of red and blue, but that means it absorbs green. It absorbs the thing it is not made of. Similarly, Yellow is made of red and green. When our eye sees the color yellow, it's because some red cones and some green cones are activated. Yellow is not made of blue. So the yellow filter lets its friendly red over here pass through. But it's not made of blue, it doesn't let blue pass. The apparent color of this is red because the white light reflects off of magenta, absorbing out or subtracting out the green. Red and blue go through the filter, or go to the filter. Red makes it through that barrier, and our brain thinks, voila, this duck is red. Okay, so let's do this again. We start with the light. Step 1, draw the color of light. Cyan light is made of blue plus green. Yellow is made of green and red. Yellow is not made of blue. So the yellow is like, you know what? We're not going to let blue pass. We're just going to let green go on to the next step. But there is no filter. So green just goes to our eyes, and our brain thinks green. For 23, okay, super easy. Specular versus diffuse. Specular is smooth. Diffuse is bumpy. Specular reflection is like a mirror. This is like my shiny car surface. This is like a puddle, something that is molecularly smooth. If you can stand in front of it and see your face in it, it's specular. But I can't take this piece of paper and put it in front of my face and see an image of my face. Examples of this: paper. You can see the white of this paper. It's not reflecting an image of my iPad here. This banana is diffuse. No matter what I do, I can't put this banana in front of my face and check my hair with it. Polarizing sunglasses are super cool. They basically work assuming that you're always working with a horizontal surface, like a puddle or the hood of a car or snow. Now, I don't ski. Let's say there's my light from the sun, and I'm going to picture my light from the sun as unpolarized, meaning its electric fields vibrate randomly in all directions. So I'm going to draw some horizontal rays. These are just representing my lines going right and left. And some vertical. Light from the sun is unpolarized, means the electric fields vibrate randomly in all directions. But when they reflect off a non-metal surface like a puddle or a snow or a car hood, the vertical polarization vector gets canceled out by this collision here. Then the vertical polarization would get canceled in the collision, leaving horizontally polarized glare. We want to block the glare. In order to block that glare, I should have a vertical filter. So here's me with my vertical sunglasses. It's like Harry Potter over here, right? With the vertical sunglasses, they block the glare because it won't let the horizontal oscillations through. Vertical filters block horizontal. Now, if this is a diverging lens or mirror, we are being tricky. If it's a diverging lens or mirror, that means this focal length is actually -15. But hey, that's a thing that would be worth writing down in case we try to trick you again. So DO is 10. And we're gonna lensmaker's equation this. So that's 1 over F is equal to 1 over DI plus 1 over DO. That's 1 over -15 is equal to 1 over 10 plus 1 over DI. And sometimes you'll see me like change where DI and DO are. That doesn't change the problem. Least common denominator is 30. That's -2/30 is equal to +3/30 plus 1 over DI. Subtract 3 to the left. That's -5/30 is 1 over DI. Cross multiply that. DI is equal to 30 over -5. And DI should come out negative because I am expecting for any diverging device a virtual image. In fact, for any diverging device, Virtual is always upright, is always smaller. M is equal to negative di over do. That's negative 6 over 10, positive 0.6. No units on magnification. So smaller because 0.6 is smaller than 1, upright because it's positive. Real images are only formed by converging. It says real, so real image is real. Let's calculate the focal length. O is 20. DI is 30. Least common denominator is 60. So that's 1 over F is equal to 3/60 plus 2/60 or 5/60. Inverse that. F is 60 over 5. F is 12 centimeters. I expect this number to be positive because the focal length for a converging device is a positive number. Magnification is negative di over do. That's negative 30 over 20, negative 1.5. And I kind of expect that. So 1.5 means larger. Remember how I said we're not going to be asking you to draw your own ray diagrams, but we would like you to be able to interpret existing ray diagrams. So let's check to see if this one is correct. For lenses, one ray goes in parallel and diverges away from the focal point. In parallel converges towards the focal point. In parallel towards the focal point. We're good. Ray number 2 goes from the top of your object through the vertex. So we're good. Top of the object through the vertex? Yes. Top of the object through the vertex. Excellent. So now you just have to draw and classify the image. See how these two solid line rays are not meeting up? That automatically means it's a virtual image. Our brain sees these two diverging rays and thinks, brain, that must have come from back here. Light goes in straight lines. That image has the top of this arrow at the intersection of those two dotted lines. And that makes that virtual is always upright, and this one is smaller. A diverging device always makes a virtual upright smaller image. But virtual images don't just have to be smaller. Virtual images can be larger. Take this one for instance. These rays don't meet up, but where our brain sees these two extrapolated back from is higher off the principal axis. So our brain thinks the top of the arrow is here, making an upright, larger image. Converging lenses and converging devices can make larger images. Hey, those two rays do literally meet. So since they do literally meet, real image, these two rays literally meet. Real is always inverted, and it's kind of hard to see here. This is supposed to be approximately the same size. We will make it very obviously larger or smaller, or very obviously the same size. Hard to tell in that one. Mirrors are a little bit different. For mirrors, your ray goes parallel in and towards the focal point, parallel in towards the focal point, parallel in towards the focal point, parallel in away from the focal point. That's my blue rays. So ray number 1 looks good. And notice that ray number 2 now does not go to the vertex anymore. It goes to the center of curvature. So top of the object, center of curvature, top of the object, center of curvature. We're good. Top of the object, center of curvature. So all these ray diagrams are good. Now we just got to interpret them. These red and blue rays literally meet. And since that's where the head of the arrow is, that is inverted, real, smaller. It's real because they literally meet. It's not dotted lines. Real is always inverted, and it's smaller than the original object because you're really far from the mirror. The farther from the mirror you are, the smaller that object appears. This one appears really big. This is actually somewhere off the page over here. Kind of ran out of space. They literally will meet up. So that's real, therefore inverted, and that's larger. Because if that's the tip of the arrow, and the foot of the arrow has to stay on this principal axis, This is a significantly larger image than object. A converging mirror can make an object look large if it's close to the focal point. So it's close to the focal point, it makes it look large. And if you pass the focal point, it's still close to the focal point. It still makes it look larger. But now it's virtual. And it's virtual because these two solid line rays do not meet. Our brain thinks they came from back here. The dotted lines are the one intersecting, making this virtual. And plus, it's upright. So I guess even if you can't figure out the difference between real and virtual, if the image is upright, you know it's virtual. That's larger. If your object is close to the focal point, it makes a larger image. Unless it's convex. If it's convex, or at least in this case, if it's diverging, you know it's always virtual, upright, smaller, which I can tell because virtual, these two rays don't meet. Upright, because virtual is always upright. That's your security mirror, side view mirror question. Let's say I wanted to do an application. We want to create an upright image. That's a virtual image. That's magnified by a factor of 3. So mathematically, what I'm seeing in my head here is m is equal to positive 3. There's only certain devices that can make positive magnification. A positive magnification is going to come from a virtual image. Virtual upright images that are larger can only be made by converging device. So either or, but since this specified lens, then just a convex lens. Now, you determine you need to place the photograph 10 centimeters from the lens in order to get that positive virtual magnification. And we're trying to find DI. Let's see what we actually know. We know m is equal to positive 3. We want to find DI, and we know DO. DO is 10. So I'm actually not doing Lensmaker's equation here. I'm going to substitute 3 for m. Negative DI over 10. So DI is equal to negative 30 centimeters. Negative is totally fine because negative indicates virtual image. And the focal length for this then, now we would use Lensmakers because now we know DI and DO. That's 1 over f is equal to 1 over negative 30 plus 1 over 10. Let's least common denominator that to 30s. That's negative 1/30 and positive 3/30 leaves 2/30. Focal length, then 1 over f is 2 over 30. Therefore, f equals 30 over 2. Take the inverse of both sides. F is equal to positive 15, which is what I expect, because if this focal length is positive, then this device has to be converging, and it is. Finally, number 30. I would suggest, guys, these are good pictures to have in front of you. That way you know what each part is. So in this case, the cornea is number 8. It's this big bump that you can feel in your eye. The pupil is the hole right there. That's number 9. 10 has to be the iris. That's the part that's colorful in your eye. It opens and closes that pupil, letting in more or less light in as needed. Then light hits the lens. That's number 7. And the ciliary muscles, number 6, open and close that lens. So then, let's say light comes in. It bends slightly going through the cornea to make it through the pupil. The lens focuses it even more to form an image on the back of the retina. Well, let's cancel some of these out. Optic nerve is number 1. Looks like retina might be number 4, because it's that whole yellow in the back of the eye there. Sclera is number 5. It's that white shell that holds your eyeball together. Fovea is number 3. That's that spot where your visual acuity is highest, where it has that large concentration of cone cells, allowing you to have detailed and color vision. And the optic disc is a little bit tough to see. This circle right here. where all of those nerve cells are stringing together to go up the optic nerve. Optic disc is 2. Okay? So, now we're trying to assign these vocab words into what they do. In order to focus the light to enter the eye, the ciliary muscles, they pull on the lens. This changes the shape of the lens and adjusts the focal length to be either forward or backward depending on what's needed. Oh, I said that funny. Okay, gotcha. Ciliary muscles change the shape of the lens. The cornea it's asking for the other part of the eye that focuses light. Both the cornea and the lens use refraction to form that real image on the back of the eye. So, wrote that wrong, my bad. Carries that optical information to the brain. That would be your optic nerve. Changes the size to control the amount of light entering the eye as the iris muscles relax and contract the pupil. The pupil is just a hole. Think of the iris as like opening and closing a window to let more or less light into a room. The retina contains both the rods and cones. That's this sensitive area at the back of the eye where the image is formed. The fovea contains only cones and produces human color vision. And the blind spot is number 2, the optic disc. The optic disc is where all those nerves come together, so it doesn't have rods and cones in that one little tiny location. So even if a clear image forms on it, there's nothing there to collect the light, so it doesn't get sent up to the brain. Best of luck tomorrow. See you soon.